just 0. All right, so this is just a 0 divided by whatever you have in the denominator. So it's going to be 5t squared. So in the end, it's going to be 0. So if I want to go for another very popular path people usually choose, which is on y-axis. So my x is equal to 0, which will exactly make the fraction vanish again. All right, so the whole fraction will be equal to 0 divided by 4y squared. So in the end, I'm getting a 0 again. Exactly the thing we talked about happens. I have two different passes, but when I plug in this function, I'm getting two same limits in the end. So this problem is to prove this limit does not exist. We have to go further. Am I right? We have to go further. For instance, we can go t goes to 0, 0 as 0 goes to, I'm sorry, as t goes to 0. So this is going to be limit t goes to 0. We have t multiplied by t divided by 5t squared plus 4t squared. So I have a t squared and 9t squared. So in the end, I'm getting a 1 over 9. Are we done yet or not?
Mm-hmm.
Yes. Are we done yet or not?
No.
Do we have to go any further?
No.
You don't need to go any further. As long as you have two different limits, you are already done. You have a 0 and a 1, 9. You are already done here. So it is sufficient to justify the limit does not exist. You can indeed go further, and especially for this type of different straight lines, as I said. These ones will be very powerful when you want to prove the limit does not exist. Think about that. If I want to prove the limit does not exist according to this type of family of straight lines, I plug in this t and kt. That fraction will be depending on the k value right here. All right? Will be depending on the k value right here. So I'm choosing different passes according to different slopes. Every different slope will give me a different value over there. Indeed, you can use this family to produce a whole bunch of different limits. Are you with me? A whole bunch of different values. However, in order to prove it does not exist, two different values will be sufficient. You don't have to go any further. Okay? Then you can say because you have different values coming from different passes, then this limit does not exist. All clear? So this class is actually super easy. If you want to find the limit of a function, you have to have a fixed point in the very beginning. All right? You have to have a fixed point in the very beginning. You don't have to require this point to be in the domain. Okay, you don't have to require this to be in the domain. If it is in the domain, everything is nice and easy. If it is in the domain, because all the functions we see in this class, the functions are all continuous in the domain. So if the fixed point is in the domain, you just plug in the value. That's exactly the limit. Things will get messier if the point is not in the domain. As we see in a couple of more examples. Then you cannot use continuity to justify the limit. We don't have to do the problems to prove the limit exists and evaluate that if the point is not in the domain. The only thing I require to do is to prove it does not exist. Then the problem is going to be much easier. You just need to find two different passes arriving at two different numbers. And these two different passes usually will come from this type of straight lines. Okay? So these straight lines are passing through the origin with different slopes. By choosing different slopes, you're getting different passes. And you can arrive at two different values eventually. Okay? So the very last type of questions you will see in this class is to modify the problem of finding the natural domain a little bit. So you will see the questions looking like this. Find the set where function f(x,y) is continuous. Okay? So I give you a function defined by a particular formula, and then I want you to find a set where the function is continuous. Okay? For example, I have a function f(x,y) is equal to x cubed plus 3x squared y squared plus y squared. So basically, I want to find a set where this function is continuous. It is slightly rewarding from what I made a remark over there. I said polynomials, rational functions, logarithm functions, trig functions, all the functions we see are all continuous at their natural domain, which means the problem of finding the set where the function is continuous is equivalent of finding its natural domain. That's all. Okay, this function will be continuous at its natural domain, which is just R2. And remember, as long as you have two independent variables, it has to be a region. Again, so if I have a function fxy is equal to x squared plus xy minus 8 divided by x squared plus y squared plus 17. Okay, I want to find the set where this function is continuous. It is equivalent of finding its natural domain. The only restriction you can draw from this fraction is the denominator is not equal to 0. So the restriction I should have is x squared plus y squared plus 17 is not equal to 0. All right, you need to solve this inequality and find a restriction on xy. However, this inequality seems a little bit weird. And it's weird because I always want you to remember, seeing the square, remembering it is non-negative, or you can just think of it as a positive quantity. So positive, positive, positive is never going to be 0. So this restriction is trivially true for all the pairs of x and y, all right? So the natural domain for this fraction is just R2. It is R2 because this restriction does not give you anything for xy. Okay, now I give you a follow-up question. So what is the limit of the function xy goes to 0, 0 of this function? X squared plus y squared plus 17. What do you have? Is equal to whatever you got the value when you plug in, all right? Because the domain of this function is all the pairs of real numbers. So no matter what you are evaluating, you can always do the plug in, okay? So 0, 0, 0, 0, you're getting minus 8 divided by 17, okay? And the very last example on the DP wall, we're going really smoothly today. So I have function fxy equal to 16 divided by x to 4 y squared plus 25. Okay, I want to find the set where this function is continuous. Equivalently, we need to find its natural domain, and the only restriction you have is x to 4 y squared plus 25 is not equal to 0. I have a multiplication of two factors. It is not equal to 0 if and only if both of them are not 0. All right? If you have a multiplication, the product of two factors, one of them is equal to 0, the whole product has to be 0. So if it is not equal to 0, neither of these two have to be 0, right? So this guy, again, will play around with the same principle. I see square, I know it's positive. So positive, positive. This factor will never be equal to 0. So the only restriction we have for the whole inequality is x to 4 is not equal to 0, or x is not equal to 0. So this is the only restriction we have. Okay? This is the natural domain. But I have to put this natural domain into a region. All right? I have to put this into a region, which are all the points on R2 such that x is not equal to 0. Okay? Such that x is equal to 0. Remember, all the restrictions you have, all the inequalities or equations you have about x, y, essentially you're looking at pairs of numbers. You still have to translate it back into a region on the xy plane. If you're only writing x equal to 0, x is not equal to 0. On the real line, this one defines a union of two intervals, right? From negative infinity to 0 and 0 to infinity. If I'm writing this as the domain of a function, I'm actually looking at the domain as all the pairs of real numbers deleting x is not equal to 0. What does this define? x is equal to 0 defines the y-axis. So if x is not equal to 0, this is all the R2 deleting y-axis. Okay, right? This is all R2 deleting y-axis. So this is going to be the natural domain of the function, and it is also the set where the function is continuous. Okay? So this is pretty much all I want to talk about today. Our main goal is to find the limit of a function for a given point. If the point is in the domain, nice and easy. If the function is, if the point is not in the domain, finding hazards. And also remember, all the functions are continuous in their natural domains. And in your online homework, you will be seeing a lot of pictures about this function. I have a very important principle throughout the semester. These pictures are very useful, but you don't have to use this. Okay? When you evaluate the limit of function, you just stick with our principles. You don't have to use the graph. You can use the graph to justify why the function does not have a limit at this point. You can use the graph to help you understand why it doesn't. Right? Remember, if the function does not have a limit at a given point, usually means this function does not well behave at this point. It can be translated, it can be verified from the picture. You can see the picture that this function will oscillate violently at this given point. That's usually a big sign for the function to fail to have a limit at a given point. However, if you want to find a limit, you want to justify limit does not exist, you don't have to use the graph. Are you with me? So if I give you a problem in a test or in a final, you don't have to draw the graph to justify the function has or does not have a limit. You only need to do the computation. Okay? So beginning from Wednesday's class, we'll talk about the real calculus. Okay, so we'll define what a derivative is, we'll define all the rules of computing derivatives, and because we have two independent variables, we have to specify our derivative is with respect to one of the variables. So this is the partial derivative, and then we'll talk about what these partial derivatives mean on the graphs. How do we use these partial derivatives in applications? It will be super fun. Okay? So see you on Wednesday.